So, in the last lecture we looked at the definition of valuations. This is a map from a field to non-negative real numbers which satisfy 4 properties. Valuation of 0 is 0, valuation of any non-zero number is non-zero, valuation is multiplicative, and then there exists some a such that valuation to the power a satisfies triangle inequality. We saw examples of valuations on rational numbers. So, today we are going to see examples of valuations on any number field, and then we are going to prove in today's lecture as well as next lecture that these examples that I give today are all the examples up to equivalence. Okay, so example. Let me write it as 3 as a continuation of what we did last time. So, let K be any number field and let sigma from K to C be an embedding. Okay. Then valuation of alpha I can define as mod of alpha sigma alpha. This is now sigma alpha is a complex number, I can take its mod, right. So, here is a exercise if you like, it is an easy exercise, and I should have said this last time as well for rational numbers, but this is an Archimedean valuation. So, it is clear that it is Archimedean. Okay. So, that is one example. Now, last time, let me take you to the last slide. This is the reason I put this Q inside R, because that is the only embedding of rational numbers into complex numbers, this inclusion of Q in R, and so this is also an Archimedean valuation. Okay. So, we are going to prove that any Archimedean valuation is equivalent to one of these things in C, right. But we can, and then what I should have said last time as well is the second example, I gave exercise for you to show that this is a valuation, but this is a non-Archimedean valuation. Okay. So, here is your first example of a non-Archimedean valuation, where this distance of, when you keep adding 1 to itself, its valuation does not go up. It can sometimes go down actually, but it does not go beyond 1, it does not blow up. All right. So, what is the second example? So, let P be a non-zero prime ideal in OK, K is again a number field. Let alpha be in OK minus 0, right. So, there exists M in natural numbers union 0 such that alpha belongs to P to the M, but not P to the M plus 1. So, there exists a unique M like this. Then p-adic valuation of alpha is defined, you can define it to be norm of P to the minus M. Okay. And then you can extend it to K by putting, so if alpha is in OK, 1 by alpha is simply OK. So, you can define it this way, right, and then multiplicatively. All right. So, again an exercise. This is a non-Archimedean valuation on K. Okay. And as I told you, these are all the examples of valuations. So, let us start proving this first. So, theorem, let K be a number field and let this be an Archimedean valuation on K, then there exists sigma from K to C and a constant such that valuation of alpha is mod of sigma alpha to the C for all alpha in K. Okay. All right. So, so this tells you that any Archimedean valuation is equivalent to this example 3 here, pretty much, right. Proof. Okay. So, if we want to prove this, you know, this better even be true for valuations of you know, integers first. This valuation of m would be mod of m to the c, right. So, if m is positive, then it should be m to the c. So, that is going to be our first claim. Okay. All right. So, claim valuation of m equals mod of m to the c for all m in Z and a fixed c greater than 0. Okay. So, valuation of minus m is same as valuation of m. So, it is enough to consider only positive bigger than or equal to 1, right. Okay. So, what am I going to do? This is kind of a somewhat strange, I mean, you know, what we are really doing is some sort of analysis on number field. So, we will have to use some analytic argument. This is not hard analysis, this is kind of, you know, just taking limits in some ways, etc. There are no hard estimates or anything, but the arguments are basically analytic in nature. Okay. So, what I do is I choose some m0 bigger than 1, then for any m in Z and n in N, what I am going to do is I am going to write this in M-adic basis, so to the base m0, right. So, so this is writing m to the n in base m0. Okay. So, we could start doing this argument with m0 equal to 2. So, write everything in binary, but at some point we will need the flexibility of using arbitrary m0, and so that is why we are not doing it just with 2. But for the first part of this argument we could do it even with 2. In any case, now if valuation of m0 is less than 1 or even less than or equal to 1, then what we can do is we can do the following. So, we can write valuation of m to the power n as valuation of summation I ai m0 to the power I. Now, I can use triangle inequality. So, yeah, so maybe replacing, okay, maybe I'll just, yeah, I'll do the following. So, to the power a to the power a. So, I can use triangle inequality now. This is less than or equal to summation I valuation of ai to the a, valuation of m0 to the ia, right. And now I can yeah, okay, what do I want to do? Yes, I want to see how many terms there are, and so how many, when you write m to the n in terms of in basis a, how many digits does it normally have? It has about log of m to the n digits, and so this is less than or equal to a 1 plus n log of m by log of m0, right. Right, I mean, if you take a, if you write a number in binary form, how many digits will it have? It will have roughly log of that number to the base 2, which is same as log of that number divided by log of 2. So the number of terms in this summation is equal to log of m by log of m to the n by log of m0, and I am just writing log of m to the n as n times log of m to the log of m, right. And then there is some constant a which is kind of an upper bound which comes from the digits, right. So, okay. In any case, if I take nth root of this, I get this is less than or equal to a 1 plus n log m by log m0 to the power 1 by n. And now the left hand side is independent of n. So, taking limit, we get that this quantity on the right hand side goes to 1, right. A 1 plus n log m by log m0 to the 1 by n goes to 1, right. So, this quantity is roughly like n, and so n to the power 1 by n goes to 1 as n goes to infinity, right. Right, because as n to the power 1 by n goes to 1 as n goes to infinity. This is elementary to prove, and so hence we get m to the a is less than or equal to 1, and hence this is less than or equal to 1 for all m in Z. That is a contradiction to the fact that this contradicts that this is an Archimedean valuation. Okay. Hence, valuation of m0 is bigger than 1. Right. Okay. And so m0 was arbitrary. This is what I meant by, we want the flexibility to have m0 to be arbitrary. So hence valuation of m is bigger than 1 for all m in integers m not equal to 0 or 1, or okay, maybe I'll, since we are only considering positive things, let me not complicate matters here and say for all m bigger than 1. Okay. Now, by this argument that we have we had above, we also get by repeating the argument above, by the way, here I kind of ignored one subtle fact, which was that I am using here that valuation of m0 is less than or equal to 1. So, this is I, valuation of ai to the a, and then I am replacing this by 1, right. And so, that is the reason why you do not see valuation of m0 here, but now that valuation of m0 is no longer less than or equal to 1, I have to take it into account, and what I get is this is less than or equal to a 1 plus n log m by log m0 valuation of m0 to the power a n log m by log m0, right. Again taking nth root and noticing that this first quantity, this goes to 1, we get the following: valuation of m to the a is less than or equal to valuation of m0 to the power a log m by log m0, okay, by taking nth root and n going to infinity, okay, we get this. All right. So, I can now get rid of that a, and I get valuation of m is less than or equal to valuation of m0 to the log m by log m0, okay. But I can switch the role of m and m0. Valuation of m0 to the log m by log m0 is less than or equal to valuation of m. Hence, valuation of m to the 1 by log m is equal to valuation of m0 to the 1 by log m0, right. So, this quantity valuation of m to the 1 by log m to the power 1 by log m is independent of m, okay. So, we choose c greater than 0 such that valuation of m to the 1 by log m, and this quantity now does not depend on what m you choose, you take c to be this, which means that c is log yeah, I don't know 1 by log m log of valuation of m. Right. Then we get what we want. Right. Then valuation of m is equal to mod of m to the power c. Okay. Any case, so once we have this, right, okay, what do we get next? So this proves the claim. Okay, all right. So now next we want to do this for arbitrary elements in K. So next we take alpha in OK. Again, it's enough to work with OK, because any element of K is a fraction in elements of OK, right, alpha by beta. Okay. So now we are going to do something sort of very strange looking thing, but this is the kind of analytic argument that one needs to use. So what I am going to do is I am going to order, right, I mean, you know, when I am considering integers, they don't, their image inside complex numbers does not depend on the embedding. So we, although this embedding appeared in the statement of the theorem here, like there exists some embedding of K into complex number with certain properties, that embedding plays absolutely no role in this first claim that I have, because image of an integer in complex number does not depend on what embedding I am taking. Okay. There is exactly one way to, there is exactly one ring homomorphism from integers to complex numbers. But now we have to take in, now when I take arbitrary element of OK, this embedding will play a part, and so that is what I am going to do. So, you know, we have to take that into consideration. So, order embeddings of K into C as sigma 1 up to sigma n, such that if I take mod sigma I alpha, then this should go on decreasing. Okay. So, there is no unique way of doing this embedding, because if mod of alpha, sigma 1 alpha and mod of sigma 2 alpha are equal, I can interchange them and I will still have this property. So, it is okay, I just choose some ordering which satisfies this property. Now, this ordering is, this ordering depends on, so this is warning, this ordering depends on alpha. So, now we are going to work with this fixed alpha to begin with. Okay. So, again I am going to choose n large enough and I am going to consider the following polynomial. So, I going from 1 to n, x minus sigma I alpha to the n. So, I write this as a polynomial x, this is a degree n polynomial plus a1 x to the n minus 1 and so on up to a n, and I am going to write P m as product I going from 1 to m sigma I alpha to the n. So, right. So, AMs are symmetric polynomial, symmetric functions in sigma I alpha to the n, right, and the largest summand of AM is plus or minus PM. It depends on the parity of M, whether you have to take the plus sign or the minus sign. But in any case, what this means is that if I take this mod of am, this is less than c times pm or c times mod of pm for some constant c depending only on n. So, something like n factorial or n times n factorial or something, it does not matter what exactly it is, but it does not depend on m and it holds for all m. Okay. Furthermore, so these are some, as I said, you need analytic arguments. So, here are some analytic arguments, but it is not very sort of, it is not very delicate analytic arguments. So, if this is less than, so if at some point the embedding makes the mod of alpha drop by something, then for n large enough, Pm dominates, whatever that means, in some, in the way that you would, I will not try to make very rigorous, it dominates all other terms of am. Okay. So, am is actually bigger than half times mod of Pm, right. So, what have we gotten? We have got half mod Pm is less than mod Am is less than C times mod Pm. So, Am essentially behaves like Pm, right. Am is some complicated sum in terms of symmetric polynomials in these sigma I to the alpha to the n, and Pm is just one of those terms. But as far as size of Am is concerned, it behaves more or less like Pm. That is what this means, right. Okay. So, so what do we get? Well, and by the claim as Am is in Z, what we get is that mod of Am is actually mod of valuation of Am is actually mod of M to the C. So, here is another kind of delicate argument. If sigma I alpha to the C is bigger than, valuation of alpha is bigger than sigma I plus 1 of alpha to the C for some I, then you see, if I take if I take product over I going from 1 to n, alpha to the n minus sigma I alpha to the n, then on the one hand this is 0, but on the other hand this is alpha to the n plus a1 alpha to the n, alpha to the n into n, n into n minus 1 and so on up to a n, and ai alpha to the n, n minus I is, again I am not going to make this precise here, much larger than other terms. Okay. And this is a contradiction by triangle inequality. By triangle inequality, So, you should think about this. I will write this better in the, I will give more details in the notes, but it is not very illuminating to do it here. Okay. So that is what we get, that yeah. So this means that so you know, so if this valuation of alpha is sandwiched between two things, we get a contradiction, and similarly get a contradiction if valuation of alpha is bigger than sigma 1 to the c, or valuation of alpha is less than sigma n alpha to the c. Okay. All right. So, there exists some I such that valuation of alpha is mod of sigma I alpha to the c. So, this is kind of what we wanted, but this is for one specific alpha. Okay. Now, of course, we can do this for arbitrary alpha in this, but the ordering of my embeddings depends on alpha. So, maybe I am getting different embedding for different alphas, right, and that is a problem. So, this sigma I a priori depends on alpha. Okay. So, how do we resolve this? Well, we notice two things, right. So, we get, yeah, so maybe this is I again will give more details in notes, but you get same sigma I for alpha and alpha beta to the n, and then you get same sigma I for beta and alpha beta to the n again. So, you have to use the same argument 3 times, and this is what you get. Hence, sigma I is independent of alpha, right, and so that is why we get the theorem. Okay, so that is a bit hurried at the end, but today what we did is we looked at examples of valuations on number fields, and then I told you the fact that these are all the valuations up to equivalence, and we kind of more or less proved that for the Archimedean valuations on number fields. So, in the next lecture we are going to consider non-Archimedean valuation on a number field, and we are going to again prove the same thing, that it's given, it's equivalent to one of those things that we looked at in the example. So, it's given in terms of a non-zero prime ideal in the ring of integers of the number field. Thank you.